So let's begin with a small example of constraint optimization. So let's say you want to build a box looking like this one, so a box without a top lid, and you want a fixed volume V. Okay, so we want a fixed volume, but we want to use as little as possible of material. So we want to use the least material. How can we rephrase that into a mathematical optimization problem? We want a fixed volume V, so that's going to be our constraints, but we want to minimize the total area of our of material that we use. So the bottom part will be x times y. We're going to have 2 times what are we going to y? Yeah, 2 times x times z, so x times z that side, and we've got 2 times this side, and we've got 2 times the other side, the y times the side of the box. Okay, so we've got here a problem that contains 3 variables, so the dimension x, y, z, and we've got one constraint that the total volume of your box is equal to a given value v. Okay, so one naive way, and actually probably the best way to address this problem first, is just to, well, let's see, v is a given. Probably I can express one of the variables with respect to the 2 others and the given value v, and then plug that into our function a. So let's see, we could totally do something like, so put, what could we use? We could put z as a function of the other one. So we are going to assume that we don't want x, y, or z to be equal to 0, which can't happen because in that case I wouldn't have a given volume v. We even have some unwritten constraints that all the dimensions x, y, and z have to be strictly positive. Okay, and then if I use this, I'm going to have that A, my total area, is going to be x times y plus 2x times v over x times y plus 2y times v over x times y, which would be rewritten as xy plus 2v over y plus 2v over x. And probably you know how to solve that, because this is exactly the kind of thing we did in the previous section of the chapter. Okay, so so this is absolutely doable. So maybe you can take some time to work on that. But just to show you one thing, we began with 3 variables and 1 constraint, and we changed that into a problem that contained only 2 variables and no constraints. Okay, and so actually this is quite the idea that we're going to have. When we have some constraints, actually we have less possibilities for the feasible set. For, well, you're going to discover what is the feasible set or the admissible set. We have less possibilities of candidates for optimum values. So in some sense, it's reduce the problem that you're looking at. Okay, so this is what we've been doing. We transformed our 3 variables and 1 constraint into a problem with 2 variables and no constraints. Okay, so a bit of vocabulary now. It's again going to be what is called an optimization program. The program name comes from historical reasons. It was called an optimization program. And so if you hear about nonlinear programming, it's not about computer programming, but really it's about optimization. You've got nonlinear programming, which is what we are doing at the moment, and you have linear programming, which is also a very important topic that we may have some time to talk about this year, but which is when the function you want to optimize is actually linear, and you've got a bunch of linear constraints that go together. Okay, and so our problem is going to be presented like something like this. We've got a problem, we want to minimize or maximize some function subject to some constraints that and a finite number of constraints given over the x in Rn. Okay, so let's see a bit more of vocabulary. So the function f is called the objective function or target function. So this is something that you will commonly see. The target given is the formula of your function defined. Something that may have surprised you is that we express the constraints like this. In our example, our constraints was expressed as x times y times z is equal to v, which is not 0, obviously. But of course, I could rewrite this as x, y, z minus v is equal to 0. So that with that loss of generality, we will always write equals to 0, but it could absolutely be something else. It doesn't change anything in the way we resolve this problem. Okay, so with that loss of generality, all constraints can be viewed as equal to 0. And all points that are satisfying the constraints, that's what we cited just before, are called the admissible set. So here on that small sketch here, you've got a first example of visually what it could be to solve an optimization problem. So you are given some function f of xy, in that case, two variables. So you're a real function, so you know it makes that smooth surface that we have here represented in R3, so the surface we've got here, and and so the colors, and we also see the heights for the value that your function f is having. And so that would be your f function that you've got here, and you need some constraints, and that constraints in our case would correspond to g of xy is equal to 0, so that's thing looking like a circle in the plane xy. So of course your constraints concerns the variables that you have. So my function f has variables x and y, so my constraint is going to be about x and y, and for instance here it's probably something like x squared plus y squared is equal to 1, or whatever the value of this is. So that's your xy are belonging to some ball, some circle centered at 0. So this is it. So if I want to express that again as equal to 0, I would make -1 is equal to 0. All right, so this is the points that belong to my constraints, and they are called the admissible set or feasible set. So we are only going to look at the values that the function is taking for the points that belong to these ones, okay? I'm not interested in anything else because this is the requirement. My points have to belong to this curve, okay? So you have on the sketch here, you've got this curve, the black one here, that actually corresponds to, is trying to show the image of the points that belong to the image of all the xy that belong to my constraints. Okay, so to all the xy that belong to this circle, and it's going to give you this image. And you see that if I look at all the values that I have for these images, I'm going to have some greater or lower values. And what we are looking for in those constraints optimization problem is what would be the highest value. And here we see that we probably have two values that correspond to the same highest value, and what would be the lowest value that I get. Okay, yeah, yes, one they have, this is the z, so we have value 2, and value -2, -2. Okay, so if I want to minimize this function subject to the constant g of xy is equal to 0, the minimum would be attained in two places, square root minus square root of 2 -1 and square root of 2 -1. And if I wanted to maximize it, I also have visually, we see here on that example that we would have two other locations for that.